Hello, this video will be about relations. So first, let's focus on the terminologies. So a binary relation is a subset of A times B where A and B are sets. An element of the relation is denoted by A or B to mean that the ordered pair AB is in the relation, or A is related to B by R. R, in this case, means a set. So R could be like, let's say, A and B, such that A plus B is equal to 0. Provided that A is part of integers and B is part of the set of integers as well. So that is like an example of a relation, which is a subset of two sets, which in this case would be the Cartesian product of the set of integers and not equal subset of. Okay, and that means an example of a relation. So a relation on a set is a relation from a set to itself. So this is an example of a relation from a set to itself because it's an integer. The set of integers referring to itself. Or rather, it's a relation from a set of all integers to the same set or itself. And it contains 2 raised to n squared subsets. Why is that the case? If we have a set A with cardinality n, therefore, the Cartesian product of that set to itself would be n squared. You can verify this to see for yourself. And then, since we're looking for subsets, what operation would we have to use? If you remember from sets, this would be the power set of the set of a set, which would help you find the subsets of the set, the Cartesian product of a set to itself. So given that this is n squared, and you add the power set operation, that would make it 2n squared. Remember, for power sets, if you have a power set A, where A is again equal to n, this would result to 2 raised to n. And in this case, it becomes 2 raised to n squared subsets. So if you have 2 elements in the set, that means you would have 2 raised to 4 subsets, which is 16. And that is only for 2 elements. What more if you have 2, if n equals 4? Then that means you'd have 4 squared, which is equal to 2 raised to 8 subsets. No, that's not the case. That is 2 raised to 16, right? And this is a very large number. 2 raised to 16 subsets is a very, very large number. If 2 raised to 12, I believe, is 2048, what more 2 raised to 16? So that is how much subsets you can get when n equals 4, or the number of elements in your set is 4. So now we will proceed with the properties of relations. So first we have the reflexive property, where for all elements A, part of the set A, and the relation is the Cartesian product of A to its and itself. Basically, it states that for all elements A, the ordered pair AA is in the relation, or an element is related to itself. To find a counterexample for this, you apply the Morgans to the entire statement, and you'd get there exists an element A where an ordered pair AA is not in the relation. So an example would be here, given A, which contains elements 1, 2, 3, 4, and R is the Cartesian product of elements A and itself, is the said relation reflexive. So our target is that all ordered pairs of the form AA must be in the relation. Since 1, 1, 2, 2, 3, 3, and 4, 4 are in the relation, then the relation is reflexive. Because if you apply the Cartesian product, you'd get all sorts of, you'd get 16 values of ordered pairs. So you have 1, 1, 2, 3, 4, 2, 3, 4. And the contents of the relation would be all 16 elements over here. Although I'll not list all down, I'll just mark those that are part of the relation, like so. And then we also have elements 1, 1, 2, 2, 3, 3, and 4, 4. And because this satisfies the said condition for it to be reflexive for all elements A, which are part of the set, so 1, 1, 2, 2, 3, 3, 4, 4 are here, then the relation is reflexive. So next we have is symmetric, where for all elements A and B, if the ordered pair AB is in the relation, then the ordered pair BA is also in the relation. An element A is related to B implies that B is related to A. And to find the counterexample, again, apply De Morgan's rule and material implication to get the counterexample statement. So here we have the same example from a while ago, and the rule for it to be symmetric. Our target is that all ordered pairs of the form AB and BA must be in the relation. Since there is no element BA which is not in the relation, given that AB is in the relation, then the relation is symmetric. So now let's redraw that same table that I did a while ago, this time accounting for all the elements in the relation. So that would be 1, 1, 2, 2, 3, 3, 4, 4, 1, 2, 1, 3, and 1, 4, 2, 3, 2, 4. This may take a while. Please bear with me. This is 2, 1, 3, 1, 4, 1, 3, 2, 4, 2, and 4, 3. So what we need to look is for all elements A and B, if AB is in R, then so is BA. So first of all, we already have the elements 1, 1, 2, 2, 3, 3, 4, 4 here. And that's actually, well, part satisfies, at least for now, that the said relation could be symmetric because we have 1, 1, 2, 2, 3, 3, 4, 4, where A is 1, B is 1, and then if you swap then, it's also in the relation. And so it goes for 2, 3, and 4. Now let's look at the other elements where A and B are not equal. So we have 1, 2 in the relation. Does that mean that the BA is also in the relation, or 2, 1? Well, since our relation consists of the Cartesian product of A and itself, one of these is one of the elements in that relation would be 2, 1. And since 1, 2 is also in the relation and 2, 1 is in the relation, it satisfies this property. And then 1, 3, and 3, 1 are also here. 3, 2, and 2, 3 are also here. 1, 4, and 4, 1 are here. 2, 4, and 4, 2 are here. 4, 3, and 3, 4 are here. And because that all of them satisfy the set condition, we can say that the relation is symmetric. Because there is no, you cannot find an element where AB is in the relation and you can find all elements AB in the relation and there are no elements PA which is not in the relation. So therefore this one is symmetric. So now let's proceed with the next property, antisymmetric, which states that AB is in the relation, BA is in the relation, implies that they are both equal, where no pairs of distinct elements exist. And we will now proceed with the example. And here's the counterexample for the antisymmetric property to determine if something is not antisymmetric. So given the same example, our target is that all ordered pairs of the form AB and BA are in the relation provided that A is equal to B. Since there is an element BA in the relation and AB is also in the relation where A is not equal to B, then the relation R is not antisymmetric. So how do we check for that? We can already show an counterexample here. So we have 1, 2 in the relation. We also have 2, 1 in the relation. And we are supposed to say that 1 is equal to 2. But they're not. So, since this is false, therefore, R is not antisymmetric. Alright. And there are also various counterexamples here like 1, 3, 3, 1, 2, 3, and 3, 2, and so on and so forth. For as long as you find AB and B are present in the relation, but the A and B are not equal. And that is one of the properties to determine if something is not antisymmetric. But if something is antisymmetric, it should follow this property. So now we'll proceed with the last property of relations, which is transitivity. So basically, if AB is in the relation, BC is in the relation, that implies that AC should also be in the relation. And here's the counterexample for it, where AB is in the relation, BC is in the relation, but AC is not in the relation. So, given this example, again, our target is that all ordered pairs of the form AB, BC, and AC are also in the relation. Since there is an element AC in the relation, for all AB in R and BC in R, then the relation R is transitive. So going back to the same table that we have over here, let's try some pairs to find out whether something is transitive or not. So let's say we have 4, 1. And let's have something like 1, 3. We expect that 4, 3 is in the relation. So, based on our table over here, we have 4, 3. And that is good if you're looking for the transitive property for a given relation. And if you try out different pairs like 3, 4, and 4, 4, or let's say 2, 3, and 3, 4, you'd get all the elements that you'd want to find in the relation. And because this holds for all elements A, B, and C for this relation, therefore R is said to be transitive. So another possibility for R to be transitive is if, um, let's first review our proposition logic. So if you have true, true, false, false, true, false, true, false, P implies Q means that this is true, this is false, this is true, and this is true. So for something to be transitive, we can say that AB is the relation. This must be false. If this is false, if either AB is not in the relation or BC is not in the relation, then that automatically would make the relation transitive, as exhibited by here, where the premise, which is this one over here, is false, which would make the implication statement true. Additionally, what we showed a while ago, which is this one, where the premise and consequent are both true, then that means that it satisfies the transitive property. And it will only become false if this is true and this one is false. So that is for the transitive property. And then we have the equivalence relation, which is a relation on a set that is reflexive, symmetric, and transitive. And equivalence is denoted by A and the symbol and B, where two elements that are related by an equivalence relation. So here are some exercises regarding the properties of relations. Given the relations over here on the set of integers below, where this is every R is a subset of the Cartesian product of the set of integers. So identify whether all 6 of these relations are reflexive, symmetric, antisymmetric, or transitive. Provide counterexamples if a property is not satisfied. So now we have the relation operations. Because relations are subsets of A times B, or the Cartesian product of A and B rather, set operations apply to relations. So you can apply the union, intersection, or even the difference of sets. So here are some exercises to give you a sample. So here we have R4, which is the intersection of these two relations. R4 is the union of these two relations. R5 is the intersection of these two relations. And R6 is the difference of R2 and R3. Also, on the set of integers, identify whether each relation is reflexive, symmetric, antisymmetric, and transitive, and provide counterexamples if a property is not satisfied. So to sample one item, we'll go back here. Let's try to do R1. So R1 states that x plus y is equal to 0 and x is less than 0. So let's first determine whether R1 is reflexive. So again, for reflexive, we need to make sure that for all elements A is in relation, where A, in this case, is in the set of all integers. So how do we solve for this? We basically test all values over here. This is actually false. It's not reflexive. Why? Well, 1, 1 is not in a relation. How so? We need to satisfy the property over here. In this case, x plus y is equal to 0 and x is less than 0. Actually, yes, it is not reflexive because 1 is not in the relation. Therefore, we can say that this relation is not reflexive. So going back, we will now proceed with the symmetric property. So again, before proceeding with the symmetric property, again, a counterexample for reflexive is 1 is not in the relation because 1 plus 1 is not equal to 0, as well as 1 is not less than 0. So therefore, it is not part of the relation. Therefore, it is not the relation is not reflexive. Now, for symmetric, when we're looking for symmetric, we need to make sure that for all elements A and B, if AB is the relation, so should BA. Okay, so let's determine whether this is reflexive, symmetric rather. So let's try negative 1 and 1. That's part of the relation, and we need to imply that 1 and negative 1 should be in the relation as well. However, this would not be the case because while negative 1 and 1 is in the relation where this is our negative 1 and 1, negative 1 plus 1 is 0, and negative 1 is less than 0, so that in the relation. However, 1 plus negative 1 is equal to 0. That is good. And then we have 1, which is our x, is not less than 0. In fact, it is greater than 0. So therefore, it's not in the relation. Therefore, this one is also not symmetric because negative 1, 1 is in the relation and 1, negative 1 is not in the relation. So that is our counterexample for symmetric property. Now, what if it's antisymmetric? So for antisymmetric, we're saying that for all elements AB, where A, B is in the relation, BE is in the relation, would mean that A is equal to B. So we noticed already that it's not symmetric based on our counterexample over here. So when we apply it to here, this would actually be false all the time. Therefore, based on propositional logic, false implies true, or false implies false, will both result to true. Therefore, it is anti-symmetric. So no matter what you apply to these values over here, it would not work. Not even 0, 0, because like if I say 0, 0, it's not part of the relation, and so is its counterpart 0, 0, which implies that 0 is equal to 0, and this would be true. And if you try other values, it would also be true as well. So therefore, this one is antisymmetric. Lastly, transitive property. Where it states that for all elements A, B, and C, okay, where if AB is in the relation and BC is in the relation, therefore, AC should be in the relation. Now, if we have something like negative 2 and 2 in the relation, we cannot have something like 2 and any arbitrary number in the relation, because 2 to begin with is not less than 0. It's greater than 0, so this one would not be in the relation. So in this case, it will be pretty difficult to find for a counterexample. There would be no counterexample for this, because if we try, we cannot try reflexive numbers, because this would be false and it would make it true. So that would be true. And then if we try something like this would also be, this would make the transitive property true as well. And therefore, if you think of pairing other values with it that satisfies this condition, it would result to this relation being transitive in terms of its properties. So that is for item 1. To provide counterexamples for transitive and antisymmetric in case you are preparing for the exam, we have AB. Simply state that AB is in here in the relation, BC is in the relation, and AC is not in the relation. And for antisymmetric, we're basically stating that AB is in the relation, BA is in the relation, and A is not equal to B. So these are your counterexamples for antisymmetric and transitive properties in case a relation violates these two properties. Because in this case, for this item, we only have reflexive and symmetric properties being violated. So that is all for relations.